Welcome everybody. My name is Markus Rill and I'm the head of the Autonomous Aerial Systems Group at TU Munich. And today I'm going to present you our work on autonomous aerial manipulation. So why do we want to do aerial manipulation? And to do that, we have multiple incentives. And I just want to show you 4 different tasks that are currently done by humans that are either very tedious, very dangerous, or very repetitive. And to give you an example, what is currently done by human industrial climbers is an example that you see here, where humans do the maintenance of the rotor blades of wind turbines manually. And this has to be done every year. And we envision to do that by aerial robots in the future. One other task is, for example, here, the maintenance of power lines. And that is a task that as well has to be done twice a year. And to give you an example how this looks like if a human is conducting the maintenance of a power line is something I want to show you in the next video. So in order to do that, that's something that is again done twice a year in the US. What has to be done is to check the isolators of the power line. And this is done by industrial climbers. So if you think this is dangerous and crazy, wait for the next part of the video. So the industrial climber has to get next to the power line. And this is done while the power line is actually in operation. So of course, the physicists among you will tell me, of course, this is not dangerous, right? You just have to be at the right voltage level, and then it's not dangerous. But wait to the next part, and you'll see what the industrial climber is actually doing. So in the next step, the industrial climbers are climbing on the power lines, and then slowly crawling towards the actual towers. And the task that they have to do there is checking the isolators. And this is basically something that we in the future would like to do with aerial manipulators. So the vision that we foresee is to, in the end, have a flying aerial robot as you see it here. So what we want to have is a flying aerial platform with robotic arms in order to manipulate and to check the isolators on the power lines. But before we have this kind of platform, we have to solve several problems in the task and in the domain of autonomous aerial manipulation. And I just want to give you a quick overview of what is actually challenging if you want to do aerial manipulation. And I just now listed on the next 2 slides the actual problems that we have to solve and that we're tackling in my group. So the first one is, if you think about these kind of platforms, right? So here we just have one of the robots that we have in our lab that are actually able to fly fully autonomously. The difference, and that's the main comparison that I want to draw here, is the difference between an aerial platform and a ground robot. And it's, first of all, very obvious, right? For a flying robot, we have to always compensate actively any wrench that we apply on our platform. So imagine that we just push our drone from the side. We have to immediately compensate for that. And that is different for a ground robot. So if you have a ground robot and your ground robot is on the ground, you can just pull the brakes, and no matter how much you push, most ground robots will not move. And that's very different for the floating platforms. Then secondly, as we have a flying platform, our positioning and as well our sensing is significantly more noisy. And thirdly, we have a dynamic coupling between a manipulator and our flying platform. And that's something I want to show you here. So if you, for example, this is a robot from a Spanish university where they mounted a manipulator underneath the drone. And just like from Newton's law, actio equals reactio, you can imagine that as soon as you start to pull the arm of the robot, your platform will tilt as well. It will tilt forward. And that means your platform, as soon as you tilt with this kind of drones, your platform will drift away in a different direction. So this was the first challenge that we have to solve if we want to do aerial manipulations. Secondly, that comes just inherently from the fact that our platform is flying. We have or we're acting in our control on a different dynamical layer. And what do I mean with that? Again, if you think about a ground robot, what you usually control is the acceleration of the wheel, right? And for most robots, you're interested in controlling the position of your robot. So what you have to do is just like integrating the acceleration of the wheel, so you get the velocity and you integrate that again, and then you get the position of your robot. For these floating platforms, this is very different. So what we can control is the spinning or the acceleration of our propellers. And the acceleration of the propellers integrates the velocity, which is then proportional to the force that we can generate with these propellers. And only by integrating then the force, we get to a torque that we can apply on our robot. The torque integrates to an orientation, and from the orientation we can control the position. And that makes the control of this kind of platforms significantly more complicated. Then two more additional topics that make the control of these robots more challenging, or the challenges of aerial manipulation. So in general, we need to build our platforms as lightweight as possible. Of course, if I want to, for example, stop with a ground robot, I can stop and it doesn't consume any energy. But if for my aerial robot, if I'm stopping at a position, I still have to fly, and that still draws my battery. So we have to build these platforms as lightweight as possible, and that results in the fact that we have very weak actuators, so significantly weaker actuators than you see on all these amazing robot arms here. And additionally, we have to build our arms as lightweight as possible. And that usually causes that we're having flexibility, vibrations in the end effector, and often very nonlinear behavior, because we have like different behaviors of the deformation among the different axes. And then last but not least, and this is a growing topic, we have as well, due to the fact that we have limited payload in our system, a limited perception, and a limited computational power. So again, this is as well due to the fact that we can only carry a minimum number of payload with us. So we have as well, compared to, for example, to the car, we're having significantly less sensors on board, and as well at the same time, not that precise sensors. So what we just usually leverage for autonomous aerial robots, we just only leverage an RGBD camera. That's the only sensor, including an IMU, to get the perception on board of the drone. And then the second part as well, of course, although we have to control our drones very aggressively, so usually these drones are controlled with 500 hertz or 1 kilohertz, we have a very limited computational power on board that makes it harder to use large deep neural networks. So there's as well a bottleneck, because we can't carry a high-class GPU with us and a high-class CPU, so usually we have to decide, do we either only use a GPU or do we only use a CPU? And that makes as well leveraging modern control techniques significantly harder on this kind of platforms. So as I've now talked about the problems, let me tell you a little bit about the solutions that we used to enable these kind of platforms to do amazing things. So this drone that you see here has a couple of different capabilities, and I just want to quickly list them to you and show you a video of what we're actually, with this platform, already able to do. And this is an example of autonomous navigation, so not the step yet to do autonomous manipulation, but here we're just in the domain of autonomous navigation. So the platform that you see here is tailored to do GPS-denied navigation in urban environments. So we're trying to fly in environments that we don't know beforehand and to track desired waypoints. Let me give you an example, and I hope I can pause the video because there's lots of information to see in the video. So what you see here, oh, perfect, is the drone is taking off in this starting location and is trying to navigate to the locations highlighted with a G here. But while this is happening, the drone is curious about specific objects. And in this case, the drone is curious about cars. So while it is navigating to the waypoints, it autonomously finds cars and maps them in the map environment. So you might now say, the first two waypoints were easy. The next waypoint is actually significantly harder to track because it is behind these two buildings that you see here. And the drone has to autonomously find this small pathway between the two buildings. And this was really a very narrow pathway. So the distance between the two buildings is approximately 1.5 meters. And the drone has to autonomously fly through this gap. And again, the tricky and challenging part is we use very limited sensing on board. So on board of the drone, we have a RGBD camera, which has a depth perception horizon of approximately 10 meters, while we fly with the drone 50 meters per second. So our reaction has to be extremely aggressive and reactive. So we have to basically plan our trajectory while we're flying it with a time horizon of less than 0.8 seconds to be able to stop at any time in case that we see an obstacle just in our perception horizon. Okay, let's come now to the second part, where we're more talking about aerial manipulation. And so far, the platforms that you've seen are this typical quad rotor platforms, right? So that's the platforms that you use, for example, for filming, and that many kids have at home already. If we want to do aerial manipulation, a different type of platform has evaluated, and in our group we were the first ones to design those kind of platforms, are fully actuated platforms. So let me quickly tell you the difference between these under-actuated platforms and the fully actuated platform that you see here on the image. And so the difference is, if I want to fly from a location A to a location B with this kind of a platform, I have to change the orientation of the platform to track a desired position trajectory. So if I want to fly, I first have to rotate to accelerate to the right. It's hard to hold the microphone and show it at the same time. So I have to first change the orientation to fly over here and stop there on the right side. So you see, for this under-actuated platform, we have a strong coupling between the position trajectory and the roll and pitch motion of the platform. And this is different for this fully actuated platform that you see here on the top. So what we have here, we're having now 6 rotors compared to the 4 rotors, and these rotors are smartly tilted. So we can actually generate a force vector in any direction. And with this gives us 3 different benefits. First one, we can hover with any orientation. So we can just fly there with an arbitrary orientation. Second one, we can, for example, translate with an arbitrary orientation. So if we want to fly from A to B, we're suddenly able to fly always horizontal. This is nice if we want to do trajectory tracking, precise trajectory tracking, but for manipulation, there's even a more important benefit. So imagine we have a wind gust happening on this kind of a platform, and imagine that this platform would even have a robot arm underneath it. Right? So underneath the platform, we have a robot arm. For an under-actuated platform, the problem is, if we have a wind gust, we have to first change the orientation to compensate that force. So we have to first rotate to fight against the wind gust, but this is even causing an error of the position of my robot arm that is even higher, right? We're multiplying that on the lever of the arm itself. And that makes control of an end effector extremely hard for these platforms. For a fully actuated platform, we can directly generate a force vector opposing the wind gust. And we don't have to do this orientation or change of orientations. So if you want to try to fly these kind of platforms, visit us on our booth over there, where you can try to pick an apple with this kind of a fully actuated platform. And before we come to an end, I just want to show you a similar platform. Basically, that is the first version of this fully actuated flying platform of a previous project, where the goal was to do maintenance of oil and gas pipelines. So what you see here in the tip of this rigid end effector is an eddy current sensor. And this eddy current sensor can measure the thickness of coatings of pipelines. So basically what the goal was is to have this end effector always perpendicular to the pipeline. And let's start quickly the video. So the goal is always have the end effector, when it touches the pipeline, to be perpendicular to the shape of the pipeline, and then scan with the eddy current sensor the thickness of the coating. And that's basically what we've done there. We as well maintained a desired force when we touch this platform, and you can see how we can actually now slide along this platform while we're in contact, apply a desired force, and keeping the sensor always in the orientation we want to have. We're doing many more things in my department. This is the people that were currently working in my group. And if you want to see other works that we do in our group, just come by at the booth. And as well at the same time, we're of course having now time for your questions and interests. Thanks.